Alright, so this is another paper that is using few-shot learning in the setting of supervised setting, and again it is using contrastive learning. But now we are augmenting it with few-shot learning. So I'm gonna be focusing on this paper in 2021. So few-shot learning deals with small amount of data. When we have, for example, data scarcity in biomedical text, labeling is expensive, and that's why we have to work on few-shot learning. So which incurs insufficient performance with conventional cross-entropy. We propose a pre-training approach for few-shot learning scenarios, that is, considering that the feature extractor quality is a critical factor in few-shot learning. We augment the feature extractor using a contrastive learning technique. It is reported that supervised contrastive learning applied to base class training in transductive few-shot training pipeline leads to improved results, outperforming state-of-the-art for ImageNet. So there are two contributions. First, we propose using supervised contrastive learning in the first stage of few-shot learning to boost classification accuracy in mini ImageNet, also CUB dataset. Our method is referred to as SPTA following the name of combined method. The second contribution of their paper is that they say that the domain shift setting, they studied domain shift setting in which the feature extractor is trained on a different dataset and a few-shot algorithm is evaluated on a fine-grained classification dataset, showing that a large dataset is needed to overcome domain shift degradation. However, when supervised contrastive learning is applied to this scope dataset, the case without a large dataset can score higher than the case with a large dataset. So there are some typo errors. So we have the base, like any other few-shot learning, and the novel. There is no intersection between them. So we examine transductive information maximization few-shot learning algorithm. First, a feature extractor transforms an input image into embedded features. And this transductive maximization maximizes the modified mutual information between the query image. So it maximizes between the query image, mutual information between the query image and the query image feature and the query label by updating the softmax trainable. So it minimizes, as you see, the cross entropy. It minimizes the conditional entropy, and maximizes the marginal entropy. So this I here, we have two terms for that. Minimizing conditional entropy aims to make confident predictions by modeling the cluster assumption, which implies that the classification criterion should not be present in the dense regions of unlabeled features. Maximizing the marginal entropy pushes the marginal distribution of labels to be uniform. Which attempts to avoid the solution of outputting only one class. Together with the conventional cross-entropy loss, the TIM loss is defined here. So this P-in that you see is just the posterior distribution over the labels. And this PN hat here is just the marginal over the query label. The quality of a feature extractor is one of the main challenges in improving a few-shot learning algorithm. So supervised contrastive loss is computed in the low-dimensional embedding by attracting positive samples which have the same class or same copied images, and also repelling the negative samples. The supervised contrastive loss is here. So Z sub L is the low dimensional embedding and tau is the temperature. So this tau is a hyperparameter. So this is the proposed pre-training approach for few-shot learning, which consists of multi-stage training. So the first stage of supervised contrastive learning uses supervised contrastive loss and projection head with the base dataset. And the second stage, so these are the first two stages. The second stage uses conventional cross entropy with the base dataset. And this two-stage supervised contrastive learning comprises the first stage of few-shot learning. The second stage uses TIM that I explained, that is a TIM loss, and the feature extractor fixed with novel dataset to perform adaptation. If the supervised fine-tuning becomes standard supervised training and the supervised contrastive pre-training is skipped, then the entire pipeline is the same as the pipeline, the baseline that is in this reference 1. So we have two-stage supervised contrastive learning, and then we have a two-stage few-shot learning. This is a paradigm that I've seen in many papers, which is very inspiring. You do the work of contrastive learning, and then you pass it to the task of few-shot learning. So we measure the impact. If you go from source domain to target domain, we have a problem. We call it domain shift. So that's why people invented many different domain adaptation methods. And domain adaptation is just one of the several paradigms of transfer learning. So this is the method that they have used for different domains. If you go from one source to another target, we expect that one shot to have a worse accuracy. So this one is always less than 5 because we have less information. So we expect the accuracy to be less than that. And if you see that for fine tuning for one shot, they have 78